You ever wonder what makes a lemon pucker your lips sour? Or why soap feels so slippery? Well, you've just had a run-in with some of the most fundamental chemicals out there, acids and bases. Today, we're going to pull back the curtain on these substances. They're literally everywhere, from inside our own bodies to the weird atmospheres of other planets.
All right, so here's our game plan. First, we'll figure out how to tell these guys apart. Then, we're going to see what happens when they meet other chemicals, the fun reactions. After that, we'll uncover the secret to their power, and finally, we'll look at the scale we use to measure it all.
So let's start at square one. You've got some mystery liquid. How in the world do you figure out if it's an acid or a base?
We've all been there, right? That feeling after a big meal, the burn. So what do you reach for? Something acidic, like lemon juice? Or maybe something like baking soda mixed in water? By the time we're done here, you're not just going to know the answer, you'll get the chemistry behind why it works.
Okay, on the most basic level, your tongue can be a hint. Acids taste sour, bases taste bitter. But, and this is a big but, please don't go around tasting chemicals. That's a terrible idea. Instead, chemists use indicators. The most famous one is litmus paper. Super simple. It turns red in acid and blue in a base.
And we've got a whole toolbox of these chemical detectives. Some are natural, like litmus, which actually comes from lichen. Others are cooked up in a lab. But check this out. Some indicators are olfactory. They don't change color, they change their smell. How cool is that?
All right, so we can spot them. But what do they actually do? The real personality of an acid or a base comes out when you see how they react with other stuff.
So here's a classic acid move. Put it with a metal. Most of the time, you're going to get two products, a salt and a whole bunch of hydrogen gas.
And how do you know you've made hydrogen? Oh, this is a fun test. You trap the gas in little soap bubbles, and then you bring a flame near them. If you hear a sharp little pop, yep, that's hydrogen. That pop is the signature sound.
Acids also put on a good show when they meet carbonates. We're talking about things like chalk or limestone. The acid just eats it away, fizzing like crazy, and producing salt, water, and carbon dioxide.
But the most important reaction, especially for solving our heartburn problem, is what happens when an acid and a base finally meet. They basically cancel each other out.
It's called a neutralization reaction, and it's perfect. The acid and base react, and what are you left with? Harmless salt and water. This is exactly what's happening when an antacid, which is a base, calms the acid in your stomach. They neutralize each other.
So we've seen what they do, but why? Why do all acids kind of act the same? And why do all bases have their own thing going on? It's time to find out their common secret.
You might think the secret ingredient is just hydrogen, right? I mean, so many acids have it. But so do things like sugar and alcohol, and they're not acidic. The real clue comes from a clever little experiment with a battery and a light bulb.
So get this. You put some wires in an acid solution and bam, the light bulb in the circuit glows. The solution is conducting electricity. But do the same thing with a sugar solution? Nothing. The bulb stays dark. What's going on here?
Here's the big reveal. It's not just about having hydrogen. It's that when acids dissolve in water, they release positively charged hydrogen ions, H+. These free-floating charges are what carry the electricity and give acids all their signature properties.
And bases? Well, they have their own secret weapon. When they dissolve in water, they release negatively charged hydroxide ions, OH-, and that's what gives them all their power.
Okay, now that we know their secret, H+ ions for acids, OH- for bases, how do we measure how strong they are? Well, that brings us to the famous pH scale. So the P in pH comes from a German word Potenz, which means power. Think of it as a ranking from 0 to 14. Down near 0, you've got your super strong acids with tons of those H+ ions. Up near 14, you have your really strong bases. And right in the middle, at 7, that's neutral, pure water. And you can put almost anything on this scale. Down at the bottom, you've got battery acid. A little higher up, around 2.2, there's lemon juice. Tap water hangs out right around neutral, and way up at the top, you've got things like drain cleaner.
So why does this one number matter so much? Well, take rainwater. If its pH dips below 5.6, we call it acid rain, and that small change is enough to seriously damage forests and kill fish.
For us, it's even more serious.
Your body has to maintain this incredibly tiny pH window between 7.0 and 7.8 just to keep you alive. If it goes too far off, things start to shut down.
And this isn't just an Earth thing. If you want to see a chemical extreme, just look at Venus. Its entire atmosphere is basically thick, choking clouds of sulfuric acid. Talk about an acidic environment.
So, from the chemistry inside our stomachs, to the health of our planet, to the very air on other worlds, it all comes down to this delicate chemical balance. Which leaves us with one last big question. What happens when we're the ones who start tipping the scales?